Hello and welcome to section 7 of chapter 5. This is going to be about roots and zeros, and we're basically just going to be extending what we know about polynomials, and we're going to be talking about how to figure out how many zeros there are and what kind of zeros there are for polynomial equations. And then we're actually going to be able to find those zeros. So in this chapter we've talked about solving by factoring a little bit, and we've talked about using synthetic division to find factors and things like that, and depressing our polynomials to be able to use quadratic formula eventually. So today we're just going to learn some more techniques to help us narrow down what the zeros or the roots of a polynomial function might be. So take a look at this chart. When we have a polynomial function, so y equals some polynomial, all four of these statements mean the same thing. They're equivalent. They're equivalent statements. So some number c is a zero of my polynomial function. So when I plug it into the polynomial, I get 0. If that's true, that same number c is also a root or a solution of the equation set equal to 0. So instead of setting it equal to y, setting it equal to 0. If c is a 0 or a root or a solution, then x minus c is a factor. And if c is a real number, then c is also an x-intercept. That's what we've been talking about all this time. Zeros, roots, solutions, and x-intercepts, as long as the number is real, are the same. Of course, we can have complex roots that could be c, and in that case, it wouldn't be an x-intercept. And then x minus c is a factor. So look at this example here. We have this polynomial function graphed. Here's the actual polynomial function, and we can see the zeros from the graph. The zeros are -3, -2, 1, and 2. Which means that the roots are -3, -2, 1, and 2. If I have a root or a 0 that's -3, then my factor is x minus -3 or x plus 3. If I have a root that's -2, the factor is x plus 2. If I have a root that's 1, x minus 1 is a factor, and if I have a root that's 2, x minus 2 is a factor. And all of those also represent x-intercepts because they're all real numbers, -3, 0, -2, 0, 1, 0, and 2, 0. So every polynomial, this is the fundamental theorem of algebra. Yay! Every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Remember that complex numbers are the set of all numbers, real and imaginary. So linear equations on up will have at least one root, which is not a surprise, right? Either the roots are real or imaginary, but I can always find a root of an equation as long as it's not a constant equation. Okay, so example 1, notice what we're doing here. We're determining the number of roots and the type of roots. So we're going to solve this equation. So this is a quadratic equation. It's going to be pretty easy to solve. We can factor this into x plus 8 times x minus 6. And then using the zero product property, we set each factor equal to 0. And I solve. So I get x equals -8 and x equals 6. So this equation has two roots that are both real, and those roots are -8 and 6. Notice the degree is 2, and I have two roots. All right, take a look at this one, y to the 4th minus 256. This is where we'll have to go back and use some of our factoring techniques from earlier in the chapter. This is the difference of perfect squares. The square root of y to the 4th is y squared, and the square root of 256 is 16. So you have y squared plus 16 and y squared minus 16. And then y squared minus 16 factors into y plus 4 times y minus 4. It's another difference of squares. Y squared plus 16 cannot factor. Then we set each factor equal to 0. Y squared plus 16 equals 0, y plus 4 equals 0, or y minus 4 equals 0. And then I solve each of those. Notice that when I'm solving, this original one was y squared plus 16 equals 0. Subtract 16 from both sides, and then I take the square root. Do not forget the plus or minus when you take a square root when you're solving. And that gives me plus or minus 4i. So I have four roots, -4, +4, and plus or minus 4i. So these two roots are complex. These two roots are real. So this equation has two real roots, -4 and 4, and two imaginary roots, 4i and -4i. Again, my original degree was 4, and I have 4 roots. All right, I want you guys to try this one. The answer here is A, and there's the work for solving that. And try this one. This is one like the second example. Okay, in this case we got B. And there's the work for that one. Notice I got 2 real roots in 3 and -3, and my 2 imaginary roots in 3i and -3i. Okay, I just want to touch real quickly on something called double roots. A double root happens when a polynomial hits the x-axis and then bounces off instead of crossing through. So if you take a look at this equation, x squared plus 6x plus 9, when I factor it, I get x plus 3 quantity squared, right? So that's really x plus 3 times x plus 3 equals 0. How many times does x plus 3 occur as a factor? Twice. So if I were to solve each of those, I would get x equals -3 and x equals -3, which are obviously the same value. But since the factor occurs 2 times, we call it a double root. So it looks like this kind of parabola only has one solution, and it does as far as numbers go. The only solution, the only root is -3, but it counts as a double root, so it does not violate the rule that when the degree is 2, I have 2 roots. It's just that this one root counts double since the factor is in there twice. And that happens anytime in a polynomial when I bounce off the x-axis instead of crossing through it. So polynomials can have double roots, triple roots, quadruple roots, and so on. Okay, and this is just what we've been saying. If I have a polynomial equation that has degree n, I'm going to have n roots. So whatever my degree is tells me how many roots I'm going to have, or how many solutions. All right, let's take a second to look at Descartes' rule of signs. Okay, so Descartes' rule of signs says we have a polynomial function, and it has real coefficients. So the number of positive real zeros is the same as the number of changes in the signs of the coefficients, or less than this by an even number. And the number of negative real zeros is the same as the number of changes in sign of p of -x, or less than this by an even number. So that sounds a little confusing. We're going to look at an example and see how we would apply that. So the key here is when I'm figuring out how many possible zeros I have, and the key here is possible. Basically what we're doing is we're going to find out what are the possible combinations of positive real zeros, negative real zeros, and then we're going to use that to figure out how many imaginary zeros we might have. I'm going to have to look at p of x, and then I'm also going to have to look at p of -x to do so. So let's take a look at this example. Here I have the polynomial p of x, right? So how many sign changes do I have? Well, here I go from negative to positive, so that's one sign change. Here I go from positive term to a negative term, that's another sign change. Negative to negative to negative, the signs don't change anymore. So this has 2 sign changes. That's p of x, right? Remember though, according to Descartes' rule of signs, we also have to look at p of -x. So if I plug in -x to the 6th is just going to be x to the 6th, the negative one in front, so that first one doesn't change. Actually, I'll just write it all out here for you so you can see what we're doing. So -x to the 6th is just x to the 6th. So that stays as -x to the 6th because of this negative here. -x cubed, quantity cubed, is -x cubed. So that's going to change that to a -4x cubed. -x quantity squared is just going to be x squared. So that's not going to change the sign. This sign does change because it's minus -x. And then I have a -1. So this is p evaluated at -x. How many sign changes do I have? Well, this goes from negative to negative, negative to negative. Here's one sign change from negative to positive, and another sign change. So p of -x also has 2 sign changes. Okay? How do we use this information? Well, we're going to make a chart. And in our chart, we're going to have a column for possible positive real zeros, possible negative real zeros, and possible imaginary zeros. Again, this is possible. We're looking for all the possible combinations. So according to p of x, I have 2 sign changes. So according to Descartes' rule of signs, I'll have 2 positive real zeros, or it can be less than that by an even number. So I can have 2 or 0, right? I can't have -2 because I can't have a negative number of zeros. According to Descartes' rule of signs, for p of -x, I could have 2 negative real zeros or less than that by an even number. And the tricky thing about this is we have to make sure to get all of the combinations. Okay, so what is the degree of my original polynomial? 6. So that means I have to have 6 roots. So if I can have 2 positive roots and 2 negative roots, that's only 4. So how many imaginary roots would I have to have? 2, so that the sum gives me 6. If I have 0 positives and 0 negatives, I would have to have 6 imaginary roots, so that my sum is still 6. Now here's where you have to be careful. I have to get all of the possible combinations of the positives and the negatives. So it's possible that I could have 2 positive zeros and 0 negative zeros. And then, to make my total 6, I would have to have 4 imaginary zeros, so that I would have 6 total. Or again, I could have 0 positive ones, but 2 negative ones, right? And then, how many imaginary zeros would I need to add up to 6? 4. So that would give me 6 total. So even though I can only have 2 or 0 positive ones and 2 or 0 negatives, I have to do 2 positives with 2 negatives and 2 positives with 0 negatives. 0 positives with 0 negatives and 0 positives with 2 negatives. I have to make sure I get all of the combinations. And then I just use addition to figure out how many possible imaginary zeros I could have. Here's a slightly more beautiful chart that you could look at, but it's the same as the one we did basically. So notice these are all of the possible combos. There are 4 options here. I can have 2 positive zeros, 2 negative zeros, and 2 imaginary, 0 positives, 2 negatives, and 4 imaginary, and so on. These are the possibilities. So I want you guys to try that here. Remember, count the sign changes in p of x, the sign changes in p of negative x, and then make a chart. All right, the answer should be D. Okay, and here's what your chart should look like. You get 2 sign changes for p of x. You can either have 2 positive or 0 positive roots. You get 2 sign changes for p of negative x. You can have 2 negative roots or 0 negative roots. And then we use that to make our chart. So you do all of the combinations, 2 positives with 2 negatives, 0 positives with 0 negatives, 2 positives with 0 negatives, 0 positives with 2 negatives, and then you fill in the imaginary ones so that each row equals 4 possible zeros. All right, so notice what we're doing here. In the last example, we were finding the possibilities of combinations of the kinds of roots we could have. How many positives, how many negatives, and how many imaginaries are possible. Here we're actually going to find what the zeros are. So we're going to solve, and we're going to use synthetic substitution to do that. And to do this, we are going to start by making our Descartes' rule of signs chart so that we know what kind of zeros we should be looking for. So if we look here, f of x has 2 sign changes, and f of negative x has 1 sign change. So this is what my chart would look like. I can have 2 or 0 positive real zeros. I can only have 1 negative one, so that reduces the amount of possibilities I have. So that means I can either have 2 positives, 1 negative, and 0 imaginary, or 0 positives, 1 negative, and 2 imaginary. So now what we're going to do is we're going to use synthetic substitution to start investigating and finding our zeros. Since there's only 1 negative real zero and there has to be 1, it's probably an easy idea to start with negative numbers. So what I'm showing you here is me trying 3 different negative real numbers to see if they are roots. Remember that if a number is a root, or a 0, that the remainder will be 0. So here negative 3 is not a 0, negative 2 is not a 0, but negative 1 is a 0. So that gives me the depressed polynomial x squared minus 2x plus 4. And that means that one of the factors would have to be x plus 1, right? So f of x has to factor down into this. And now I can solve for the second part of my quadratic depressed polynomial. This I can solve by factoring, completing the square, quadratic formula, whatever. So here what they're showing you is the depressed polynomial, and they're solving it using quadratic formula, because this one can't be factored. So we use quadratic formula, plugging in all of the correct coefficients. And I end up with 2 plus or minus 2i square root of 3 over 2, which simplifies down to 1 plus or minus I square root of 3. So my final solutions are negative 1, which we found by synthetic substitution, and then I have 2 imaginary or 2 complex roots. So altogether I have 3 roots. Notice that was one of the combinations in my table. Okay, so I want you guys to do the same thing with this one. All right, your answer here should be A. And here's the work. Notice we ended up with 2 positive zeros and 1 negative 0. We will finish the last part of your note